Yars Revenge, one of the best-selling Atari 2600 games, has a very peculiar graphical design quirk. This busy area in the middle of the screen is known as the neutral zone, an area where you are safe from the destroyer missile, but that also prevents you from attacking the enemy. The game's developer, Howard Scott Warshaw, had this to say about the implementation of the zone. Do you know what that is? Here's a great piece of trivia. It's the actual program code laid out vertically and counter-scrolling over each other. I almost had a problem with Atari over it, because they felt it was a copyright violation to show the code on the screen. But I explained to them that first, besides the scrolling, there was some X, Y, and random color processing being done to it, and second, if somebody could get the code from that, then they deserved it. Challenge accepted. Let's see how close we could get to uncovering the code to Yars Revenge just by analyzing the graphics of the neutral zone. Retro Game Mechanics Explained is brought to you by its YouTube members, Patreon supporters, and viewers like you. Thank you. Before we get started, there's already one issue we have to tackle. If the game's code is supposedly being drawn on the screen, how are we going to be able to see it? The neutral zone almost looks just like colorful TV static and flickers very quickly. In this video, I'll be using an Atari 2600 emulator, which allows me to see perfectly crisp pixel edges and even slow down the game footage. It's going to be pretty important to be able to see each individual block of pixels here in order to even have a chance of decoding everything. So we're already starting at a great advantage compared to a theoretical someone who might be trying to do this back in the 80s. That's going to be a recurring theme throughout this video actually. The answer to, can we reverse engineer Yars Revenge code just from the video footage, is yes, in theory, but I think in practice it's going to be very near impossible. But the important thing is that it's theoretically possible, if you're very patient. Let's look at the neutral zone animation in detail. It is simply a grid of thin blocks that measures 7 columns wide and 192 lines tall, some of which may be cut off by the television's overscan. The first thing you'll notice when I slow the video footage down is that the entire screen is flickering. Essentially, it is beyond the capability of the Atari to be able to draw both the neutral zone and the quotile shield at the same time, while also drawing the quotile itself, Yar, the destroyer missile, and potentially the Zorlon cannon. I have a video all about racing the beam when it comes to Atari game development, so you might want to watch that video if you're interested in that topic. Anyway, by only drawing one of these elements at a time, the code is greatly simplified since it only has to draw half as much stuff. I'm going to just remove all of the frames in this animation where the quotile shield is drawn, so we don't have to worry about this flicker, but it is important that we are still looking at every odd-numbered frame from here on out. So here we are looking at this multicolored TV static. If you stare deeply into it and become mesmerized by it, you might eventually start to see some patterns emerge. First off, the animation only has 128 frames before it repeats. Take into account we're looking at every other frame, and that means this entire thing takes 256 frames, or about 4.3 seconds to loop. This very strongly indicates that the animation is driven by a frame counter. The counter increments by 1 each frame, and it is allowed to overflow from 255 back to 0, implying the counter is an 8-bit counter. You can even find the looping point in the animation if you happen to find the next pattern, which is definitely more tricky to notice. If you pay attention to the static, specifically the right edge of it, you might notice that you can sort of follow blobs of pixels that move up or down. This lines up with what Warshaw said in his interview, vertically and counter-scrolling over each other. If you only look at every other line, the pattern becomes much clearer. Here, let me remove the color too, if that helps at all. Now you can see that the pixels are clearly moving downwards, at least on the right edge here. The left side is still kind of a mess. If we look at the opposite set of lines, we can see the pattern is moving up instead. Someone who is both technologically inclined and has a keen eye might be able to spot the next step here right away, or at least after staring at it again for a while. I'm going to isolate only the rightmost column first. The blocks in this column are actually very stable. It seems like there is a spot here where they all flip colors. That is, a white block will disappear and new white blocks appear where there were none before. Let's mark that spot for now and look at just the next column. Now it looks like there are two special spots where the blocks will flip. Mark those down and move on to the next column. It's getting more difficult to see, but you can barely make out the 5 spots that the blocks flip in this one. Somehow the next column is a bit easier to see, and that there are 11 of these spots. The regions between these flipping points are shrinking by half each step we take to the left. If we highlight every other region, a familiar image appears. This is the binary counting pattern. If we take each of the black regions as 0 and the white regions as 1, each step downward is like incrementing a binary counter by 1. Well, in this case, the pattern is flipped horizontally, so the least significant bit is on the left instead of the right like we are normally used to. We still have a few columns to address too, but thanks to the fractalness of this pattern, we can just continue it easily. If we renumber all 7 columns with this binary counter, we get the sequence 0, 1, 1, 2, 2, 3, 3, and so on. It looks like there is a counter held in memory that is being incremented every 2 lines. However, there's a clue that this might not be the case. We only have 7 columns in the neutral zone, but bytes have 8 bits in them. And just like the frame counter, it's very likely that this binary counter has 8 bits as well. If we extend our binary counting pattern one more column, we get a different number on every line. The first line has 1, and the next ones go 2, 3, 4, 5, and so on. This makes a lot more sense, since it is very common for Atari games to have a counter to keep track of which line is currently being drawn. It's just that the neutral zone seems to disregard the lowest bit of this counter when it comes to drawing the colored static. So we have this pattern of flipping blocks that appear and disappear in this fractal binary counting pattern. What can we do with it? Well, when it comes to flipping bits, we should look towards the exclusive OR operation. This is a binary operator that takes in 2 bits as inputs and outputs a single bit as a result. The definition is often stated as something like, the output is 1 if either one input or the other are 1, but not both, hence exclusive OR. However, sometimes a better way of thinking about it is that one input is the base and the second input is the mask. If the mask is 0, the output is just the base input. If the mask is 1, the output is the opposite of the base input. So when it comes to XORing 8-bit values together, you can look at where the 1s lie in the mask and just flip those bits in the base input. In our case, let's try an XOR operation on this pattern using the neutral zone as the base and this binary counting pattern as the mask. And just like that, the flickering is pretty much gone. There is a reason why it's not completely perfect, but I'm just going to ignore that for now. I'll explain why that happens later. Now that we can see something that is mostly stationary, we can try to use multiple shots of this texture that is scrolling by to piece it together so we can see the entire thing at once. Now it may look like we have 2 blocks of data, but if you invert all of the bits of one of them and then turn it upside down, then you'll see that they are identical. What we're left with is a matrix of 254 rows and 7 columns of bits. Believe it or not, this is indeed the machine code of the 6507 assembly code that makes up the game, or at least part of it. Now, each row only has 7 bits. Like we found out before, one of the bits has been removed from the underlying data before it got displayed on the screen. So there is no way to recover what the 8th bit should be for each of these bytes. We aren't even completely certain where that 8th bit goes. Is it missing from the left side or the right side? In other words, was the least significant bit or the most significant bit masked away? Now, we can place our bets on it being the least significant bit, since that's the bit that was masked away from the binary counter pattern we saw earlier. But if we are presuming that this data is machine code, we have another trick up our sleeves. CPU machine code tends to follow a certain distribution of bytes. Each type of CPU instruction is mapped to a certain byte via its opcode. Since certain instructions are more common than others, we can expect to see more of a certain byte value than others. And some opcodes don't correspond to any official instruction, so we should expect to see them much less frequently. For example, the load from and store to memory instructions have opcodes hex A5 and hex 85 respectively, so we should expect to see them fairly often, as opposed to the indexed rotate left and right memory instructions, which have opcodes hex 3E and 7E. And the opcodes hex 42 and AB do not map to an official instruction, so we shouldn't see them very often. Now, machine code consists of more than just opcodes. There are also operands, which is why these values aren't completely non-existent. But we can use this distribution to help us figure out where this extra bit should go. Let's suppose the extra bit were supposed to be the least significant bit. We don't know if this hidden bit is a 1 or a 0, so there are two possible values that each byte could be. We can check both of them and see if the resulting values are valid instruction opcodes. Out of 256 possible 8-bit byte values, only 151 of them are valid instruction opcodes. However, I would arbitrarily only count about 78 of them to be common. I'll go ahead and check if the resulting values are common instruction opcodes as well. Now I can count how many of the data bytes we have here can possibly result in an instruction opcode. In this case, we end up with 221 valid opcodes, about 85% of them, of which 120 could be considered common, just under half. Then we can do this exact same process, except instead of treating the extra hidden bit as the least significant, we can make it the most significant. However, this setup only results in 132 valid opcodes, just over half, of which only 63 are common, about a quarter of the total. This isn't a completely foolproof method of determining which is the correct location of the extra bit, but in conjunction with the binary counter also missing its least significant bit, it makes sense that these machine code bytes would be as well. Now, before we can try to disassemble this machine code, we have two more problems. First of which is that we don't know which direction these bytes are supposed to go. Remember a little bit ago when I flipped one set of the neutral zone blocks vertically to show that the two sets are actually the same? Well, I could have very easily just flipped the other set instead. Which set is in the correct order and which is in the reverse order? We could try to analyze the machine code to try to figure out which way it should be interpreted, though it might just be easier to disassemble the code in both directions and see which one makes more sense. However, if we try to disassemble it in either direction right now, it looks like neither of them makes sense. What's going on? Well, take a look at these few bytes right here. Hex 84 and 85 are both opcodes for store instructions. Hex B1, A4, and A5 are all opcodes for load instructions. These instructions are all 2 bytes long. They each take one operand, the memory address to load from or store to. However, in this data we have, it seems that the opcodes are all one after the other with no operand in between them. Recall back again when we had the 2 sets of patterns in the neutral zone. Each set was drawn on every other line. In other words, each row in the pattern had a gap of 1 row in between them. This all points to one possible thing. The data we have here is really only half of the game's machine code. We're missing every other byte since every other line is drawn per set. This means that these opcodes all belong to instructions in the code, and that the operands of these instructions are the bytes we don't have access to. Ultimately, this means that for every 2 bytes of game code, 16 bits, only 7 of those bits are used to draw the neutral zone. Is it still possible to completely disassemble the machine code and get the original source code back? I really want to answer this with a theoretical yes, but in practice it's basically impossible. I'm going to go more into detail about trying to disassemble this machine code later on in the video. Right now I want to take a quick detour and look at the source code for Yars Revenge so we can see exactly how the neutral zone is drawn. We won't be doing any guesswork here. This is truly what is running on the Atari CPU when the game is running. Here is the code responsible for drawing the neutral zone. The snippet on the left runs for every odd scan line, and the snippet on the right runs for every even scan line. The first line is defined as line number 1, so it will run the left code, and then the right code will run for the second line, and it keeps going back and forth like this until the bottom of the screen. First, let's get familiar with the variables and memory locations that are used here. Throughout the code on both sides, the CPU's X register is what holds the current scan line number. The A and Y registers are the other 8-bit CPU registers used here. The game timer memory location is simply an 8-bit counter that is incremented every frame. Not every scan line, mind you, just every frame. So on one frame, this counter will have one specific value, and all 192 lines of the neutral zone will utilize the same exact counter value. Then when it gets drawn the next time on the following frame, it will be incremented by 2. Remember still that the neutral zone is only drawn every other frame, specifically on odd frames. So when this counter is 0, 2, 4, etc., the quotile shield is drawn, but when it is 1, 3, 5, etc., the neutral zone shows up. The neutral zone mask memory location defines which bits from the underlying data will show up on the screen. In other words, this defines the number and position of the columns of the neutral zone. The game sets this value to binary 1111, 1110, which results in the 7 columns we've seen. But by modifying this value, we can see different patterns appear. Later levels in the game disable the neutral zone altogether, and its graphics are disabled by just setting this mask to 0. PF2 and COLUPF are memory-mapped hardware registers belonging to the Atari's TIA chip. They are responsible for which pixels of the playfield are actually drawn, and what color they are, respectively. Let's look at the odd scan lines code first. First, the value in the X register, the scan line number, is copied to the A and Y registers. Then the A register is exclusively ORed with a certain value found in the game's ROM. Let's resolve this indirect indexed addressing mode here. The intermediate address is dependent on the game timer. So if the counter is at, say, hex 37, the lower 8 bits of this address will be hex 37. However, we need a full 16 bits to create an intermediate ROM address. The game timer is found at memory location hex E9 in RAM. The upper 8 bits will be derived from the byte that follows that at location hex EA. The game writes the constant hex F0 to this memory location when the game boots up and never changes it ever again. This means that the upper 8 bits of our intermediate address will be hex F0. This was chosen because the Atari will map the game's ROM to the memory region hex F000 to FFFF, which means that our intermediate address will be pointing to somewhere in the first page of ROM. In our example, the intermediate address becomes hex F037. Now we're still not done because we have to add the Y register to the intermediate address to get the effective address. The Y register has the scan line number from before. This is how each row of the neutral zone is unique. They all end up reading a different ROM value. Now notice that since the neutral zone is only drawn on odd frames, and we're looking at the code that only runs for odd numbered scan lines, we're always adding an odd number to an odd number in this step, which means we'll always end up with an even number for this pointer. This is why we were only able to see every other ROM byte earlier. Anyway, that ROM value gets fetched and finally XORed with the A register, which also holds the scan line number. This is ultimately what hides the ROM bytes from plainly appearing on the screen. Next, the A register is masked by this AND instruction. Like I said, this memory location only ever holds the constant binary 11111110, which essentially just resets the least significant bit to 0. That's why that bit was missing when we were trying to decode things. The resulting value gets written to the PF2 register, which will display the corresponding colored pixels to the screen. Additionally, here is where the randomized color effect is done as well. The upper 4 bits of the COLUPF register control the hue of the color, while the next 3 bits control the brightness. The least significant bit is unused, which was already masked away in the previous step. Here's all 128 possible colors the NTSC region Atari 2600 can display. This instruction here masks out the highest bit of the brightness parameter, which prevents the brighter colors from being able to appear. If the value fetched from ROM happens to be 0 after both of these bits are masked away, the color will be completely black and indistinguishable from the background. Remember earlier when I pointed out that there was still some flickering bits in the decoded neutral zone patterns? Those all have to do with bytes that got mapped to black. Now, when the value is 0, none of the pixels are going to show up anyway. But if the value happens to be 8, the playfield pixels get set to binary 00001000, which should display one block of color. But since this single bit is the one that just happens to get masked away before the color is applied, it ends up being invisible. Additionally, it is only the odd-numbered scan lines that define the colors of the neutral zone. This means the even-numbered lines will just inherit the color of the previous line. If the odd-numbered line has a value of 0 and becomes black, the even-numbered line after it can be anything, but it will still appear invisible. Speaking of the even-numbered lines, let's look at their code now. This code starts with a TXA instruction just like before, so the scan line number finds itself in the A register again. But then things are a bit different with this EOR instruction. This will flip all 8 bits of the A register. Mathematically speaking, this performs the operation 255 minus A, with the result overriding A. This is where the vertical flipping action comes from, since this will map scan line number 2 to 253 and scan line number 192 to 63. Now, the same instructions as the odd lines are ran, exclusively ORing with a value from ROM and masking out the lowest bit. The remaining code was a bit of a mystery at first, but there is a distinct reason why it exists. There is a branch instruction here that checks if this value is 0 after the lowest bit is erased. If the value is not 0, then it gets written to the PF2 register just like normal. However, if the value is 0, then nothing gets written to the PF2 register at all. Instead, the constant hex 5A gets written to the COLUPF register. This corresponds to a bright pink color, brighter than any of the possible colors that can be randomly picked by the odd scan lines. What I haven't shown here is that the PF2 register does get reset to 0 at the end of each scan line. So if PF2 isn't written to at all on a certain scan line, no pixels will show up anyway. Even if the color is set to light pink, there will not be pixels to color light pink in the first place. This code does have a visible effect though, but not on the neutral zone. If the Zorlon cannon is on the screen, it takes on the colors of the neutral zone. It's not part of the playfield, instead it's the ball sprite, but the COLUPF register defines the color of the playfield and the ball simultaneously. When an even-numbered scan line of the neutral zone results in 0 being drawn, part of the Zorlon cannon will show up as bright pink if it's visible on the next scan line. This had to be done so that it would still be visible even if the neutral zone is not being drawn on this level. In those levels, it will show up as bright pink stripes. Now, let's go back to the effective address of this EOR instruction. Again, the game timer is always an odd number, since the neutral zone is only drawn on odd frames. The Y register here is 255 minus the scan line number. In this case, the scan line number is always even, but when it gets subtracted from 255, the result is always odd. Then adding this odd number to the odd frame counter, the result is always even. This means that even-numbered scanlines will also always end up with an even number for this pointer. Since both the odd lines and the even lines will only read even-numbered ROM addresses, the odd-numbered ROM addresses will never be exposed in the neutral zone graphics. This also causes another interesting pattern in the neutral zone if you look close enough. Since the even lines and the odd lines read from the same ROM area, but one is just a reversed copy of the other, if you ignore the colors, the neutral zone is symmetrical vertically at the 128th scan line. The sequence of 128 ROM values that can show up as part of the neutral zone changes every frame, but each time it's symmetric, which means even as it animates, it has this reflection point about 2/3 of the way down the screen. Okay, finally, let's put our sleuthing hats back on and get back to the problem we had earlier. Just a warning that it's about to get pretty technical, and if you don't have a good grasp on how assembly and machine code works, it might be a little difficult to follow. Our problem is that we have a list of 254 7-bit numbers, of which we know the least significant bit is missing to form an 8-bit byte. We also know that we only have every other byte, and that there should be another 253 bytes, one in between each of the values we do have. What we don't know is whether this list of values should be forward or backward. We're not sure of the correct order. The easiest way to figure this out would be to disassemble the machine code into assembly code in both directions and see if one makes more sense than the other. However, it's going to be a big challenge to disassemble code when we have less than half of the total information. Let's see how we could try to do this. I'm going to start with working on the data in this order, where the binary 1001110 value comes first. First, I'm going to lay out all of the bytes, whether we know them or not, in a big long list. Each time we use a data value, there are two possibilities for what the underlying ROM value could be. In this case, if the missing bit is a 0, we get hex 9C, and if it's a 1, then we get hex 9D. I'll put both of these in the same row, since they are the same byte, we just don't know which one it is yet. The second byte could literally be anything. We have no information about what it could be at all. The third byte comes from the binary 1001111 value, so it could be either hex 9E or 9F. And the fourth is completely unknown again. This just continues onward for all 507 bytes, the 254 values we have, and the 253 bytes between them. Now we also can't be certain that the code starts exactly at our first byte here. This could belong to the middle of an instruction. We can take care of that by just adding a couple unknown bytes before the first byte we have. Alright, we have a list of all the bytes in our machine code we want to try to disassemble. Since we don't know exactly what each byte is, we have to take into account all possibilities each byte can be. So I'm going to create a chart that will show every possible instruction that could exist. Each instruction will be a box, and that box's height will indicate how many bytes long it is. 6507 instructions can be 1, 2, or 3 bytes long. The vertical position of the instruction will indicate which bytes it consists of. This will make more sense as I fill out the chart, so let's do a few. Let's start with the hex 9C 9D byte. If this were an instruction opcode, it would be an STA instruction. This is a 3-byte instruction with the opcode hex 9D. Since it's 3 bytes long, it spans across 3 bytes on the chart. The other option, hex 9C, doesn't map to a defined instruction. Technically, it can still be executed as an instruction, but I'm also going to assume here that the developers only used intended documented instructions. This means we don't have to draw a box for this opcode. Now, this hex 9C 9D byte could also be an operand itself. It could be the lone operand of a 2-byte instruction. We would indicate that with this box. We don't know what the opcode of this instruction is, and we don't even know if the operand is hex 9C or 9D, but all 2-byte instructions that fit here will be represented by this single box. It could also be the operand of a 3-byte instruction. If it were the first operand, that would be covered by this box, and if it were the second operand, it would be this one. There are now 4 boxes in the chart, which represent the 4 different possible outcomes for this single byte. Time to add a whole bunch more. Now we can start focusing on the second byte. Since we don't have any information on this byte, we don't even know if this instruction is 1, 2, or 3 bytes long, so we have to take each into account. This can be done by just drawing 3 different boxes of 3 different sizes on the chart. One for if it's a 1 byte instruction, one for a 2 byte instruction using the hex 9E 9F byte as an operand, and one for a 3 byte instruction. In fact, every unknown byte will get these 3 boxes, so let me go ahead and just fill all those in right now. From here on out, when we focus on a byte, we only have to consider if it were an opcode, since it would be considered an operand by a previous instruction that we've already looked at. Now, the third byte. This one could be a hex 9E or 9F. Now this is interesting. Neither of these bytes are proper instruction opcodes. That means there will be no new boxes for this row. The same goes for the 2 and 3 row as well. Neither of these are proper opcodes. While the byte 4 is also improper, 5 is a valid opcode, so we have to create a box for it. This represents a 2 byte ORA instruction, so it gets a box 2 rows tall. And one more row. Hex F0 and F1 are both valid opcodes, so boxes need to be created for both of them. If this instruction had opcode hex F0, it would be a 2 byte BEQ branch instruction. And if it had the opcode hex F1, it would be a 2 byte SBC instruction. Both of these get a box that is 2 rows tall. Okay, that's filled out enough for now. Let me show you how we start to eliminate possibilities. The way this chart is designed makes it really easy to follow a potential sequence of instructions. We can simulate a program counter with a little marker that sits at the top of a box. When an instruction is executed, the program counter will move to the bottom of the box of that instruction. So for example, if we start execution at this unknown 2 byte instruction, we put the marker here. If we execute the instruction, then the program counter will move down 2 rows in the chart. The next instruction to execute must start at the same vertical position as the new location of the program counter. So now we have 3 choices for what the next instruction can be. Let's choose this 3 byte instruction. We execute that instruction by moving the program counter down to the bottom of its box. Then we just keep repeating this process. But here's the catch. If we ever find ourselves stuck where the program counter is not at the top of a box, then that means we've arrived at a contradiction. That means the instruction we just executed must be incorrect. For example, look where we are now. The program counter doesn't line up with the top of any box. Therefore, this 3 byte instruction cannot be a possible option for the disassembled code we're looking for. Now, we don't have to keep track of a program counter or anything to find all these contradictions. All we have to do is look for any box whose bottom doesn't line up with the top of another box. This is essentially a dead end, and we can remove it from the chart. In fact, with what we've looked at so far, we can also remove these 3 boxes, since they all lead to dead ends, thanks to these 2 bytes that don't correspond to an instruction opcode. Another useful thing we can do is remove instructions from the chart that are either very unlikely to be correct or don't make any sense. We already have an example of this. The STA instruction uses hex 9E or 9F as its second operand here. This would mean that the upper byte of the intermediate address of the store instruction would be hex 9E or 9F. In either case, this memory location doesn't map to anything meaningful in the Atari 2600 architecture. It's technically a valid instruction, but it's very unlikely that the game is storing a value to a garbage memory location. Therefore, we can remove it from the chart. By removing unlikely instructions, we can cause a sort of chain reaction that will eliminate previous instructions. Now if you look at the chart, there are a few rows that only have a single box that spans them. This means that for that particular byte in the list, there is only one possible instruction that it could belong to. In our case here, That means these two instructions are certain to be in the final disassembly. We don't know what the opcode is exactly, so we don't know what the instruction actually is, but we know two 2-byte instructions will exist here. So this is the chart so far after looking at only 8 bytes. All we gotta do is fill it out for all 507 bytes. And then do the same process a second time where all the bytes are in reverse order, and see if one makes more sense than the other. You might be curious to know if it's possible to arrive at a true dead end where there is no possible path from the top to the bottom of the chart. Like, suppose there were so many boxes missing that a row had 0 boxes, and therefore 0 possible outcomes. Well, it turns out that's not the case, and here's why. See this sequence of 2-byte instructions? These will always be valid possibilities. We don't know the opcode for them, so we can't eliminate them by that method. And since they are all 2 bytes long, they all feed into each other like a perfect chain. This means that this is sort of like the default execution path. In the case that a bunch of instructions are eliminated in a certain region, there will always be this path of 2-byte instructions to follow. I'm definitely not going to walk through the entirety of these two charts, since they are just huge, but here they are. As you can see, one of them has some bigger chunks missing out of it. That doesn't necessarily mean that it's the incorrect orientation of the bytes, but I do think it is the incorrect one, and let me show you why. In the orientation we just walked through a bit, if we just step forward a few more instructions, we can see this set of bytes from our data. The hex F0, 8485, BOB1, 8485, A9, 8485, and E4E5. I know from my personal experience that these are opcodes for some pretty common instructions, so I would lean towards these being the opcode bytes. Let's see where these showed up in the reverse orientation, all the way at the bottom. In this orientation, all of these bytes are forced to be operand bytes. This is due to the exact same 2, 3, and hex 9E9F bytes that we just looked at that aren't valid opcodes. They create a few dead ends that end up causing a huge chain reaction which eliminates a ton of possibilities, and the only choices left are to treat these bytes as operands. It isn't complete proof that this is the incorrect version, but if I had to choose between one or the other, I would choose the orientation on the left here. Now, out of the 507 bytes here, only 73 of them are consolidated into a known instruction. And all of them are 2-byte instructions with an unknown opcode, since, like I mentioned, these types of instructions have no way of being eliminated. So, is that it then? Can you possibly work out what the original source code is from all of this uncertainty? Unfortunately, that is where my research for this video ends. With enough analysis of this chart and maybe some experience with programming for the Atari 2600, I think it would be possible to figure out maybe a few chunks of this code, but not the entire thing. There are some aspects of assembly code that would just be impossible to figure out without seeing every single byte. I mean, just imagine you are given a memory load instruction, but you aren't given what the memory location is. You can even be told that this instruction is loading, say, the number of lives the player has, but there's no way you can figure out what byte in memory corresponds to the player's life counter unless you encounter it in the code already. But say the life counter is at memory location hex 9E. Since we only have access to every other byte, if you're given a 2-byte instruction with hex 9E as the operand, you would not know the opcode. Therefore, you would not be able to know if this instruction were a load, or a store, or maybe a decrement, increment, or a compare. There's just not enough context to be able to figure out everything and be 100% certain of it. In case you are curious, here is the proper path through the chart that corresponds to the code in the game's ROM. Even given the proper path here, there are still a lot of unknowns. I'll end this video with a fun fact. Take a look at this part of the chart. Does this part of the code look familiar? This is the code we looked at earlier in the video that is responsible for drawing the neutral zone to the screen. That's right, the code that draws the neutral zone actually ends up being used to draw the neutral zone itself. I doubt that it was intentional. The neutral zone just uses the first 512 bytes of the ROM, but the routine that draws the neutral zone happens to be within those first 512 bytes. I guess Warshaw was right in that his method of manipulating the ROM data was enough to prevent anyone from deriving the game's source code. Especially back in the day, remember I used clean pixel-perfect video footage and slowdown and all of this fancy computation and automation that wasn't readily available in the 80s. I can't imagine anyone using their VCR to record a VHS tape and pausing it frame by frame to try to write down what they think the pattern is on the screen when it's all blurry and shaky. I'm not sure anyone would have the patience to do all this and actually figure it out either. Anyway, thank you for watching, and see you next time.